Good afternoon, everyone. My name's Iain Robertson. I'm a Senior Engineering Director at Tessent Embedded Analytics. Today, I'm going to talk about leveraging the RISC V Efficient Trace standard. And I'm not going to keep saying RISC V Efficient Trace all the way through this. I'm going to refer to it by its commonly the common name of eTrace. So what I'm going to cover today, so first of all, a little bit of background, I guess, why would you use trace? I'm going to cover some basics of basic principles of how tracing is done in general. We're then going to take a closer look at the eTrace standard. I'm going to dive a bit deeper into some of the efficiency options that come with that, and then wrap up with some conclusions. So, okay, so first of all, why use trace at all, really? So, understanding program behavior is not always easy. The traditional way of dealing with that maybe would be to halt the CPU, single step, and so on. But this is not always practical, particularly in real-time applications, and less so in modern SoCs, where you typically have multiple CPUs and other devices interacting with one another. So the kind of problem that you may be trying to debug or optimize may be dependent on interactions between components, and as soon as you stop, halt, those interactions disappear, and you can't figure out what's going on. So so having access to observation at full speed is really important, but that could potentially result in a lot of data that you need to extract from the chip, and so being able to do that in a very efficient way is important. Invariably, the amount of bandwidth you've got available for getting stuff out is less than you'd like. So what you need for that is a trace solution, and processor trace provides that, and allows you to do a whole load of different debugging and profiling and so on. So okay, so just I guess an example of how trace could be used, a practical example. So this came from a paper that Richard Bond from Seagate gave at the Siemens user-to-user presentation earlier this year. I stole this from Richard. Thank you, Richard. I guess in this example, they're building disk drive controllers, modern disk drives. We're talking about 2.4 nanometer positioning accuracy for the heads, and this is obviously is going to require huge amounts of real-time compute, but within a fairly constrained power and area cost limits. And so the way that what Seagate have done here is they used a RISC V processor. They coupled that to a trace encoder from Seagate from Siemens, which allowed them to fully understand exactly what was happening in their code, optimize that. There was also a cycle accurate capability in that particular encoder, which allows the tight loops to be really optimized down. And as a result, for one of the key metrics, they achieved a 3x reduction in the computational cycle. So a good example of how trace can be used in practice. So how exactly is trace usually implemented? So fundamentally, there are two key components in a trace solution. One is an encoder, which would be hardware on the die connected to the CPU. That's monitoring the instructions that are executed, encoding and compressing that, and then sending that typically off chip, to a decoder, which is a software which will use that information along with the program binary to reconstruct the execution path through the program. And the most common form, I guess, of this is called processor branch trace. And in this context, branch means any non-sequential change in the program. It's not just branch instructions. Using this approach, you can achieve a very high compression, and high compression means you can trace more. Either if you're tracing into a buffer, then you can get more information in there. Alternatively, you may be able to trace more cores at the same time. And eTrace is a form of processor branch trace. It also includes some additional optional modes which offer even higher compression, and as well as some debugging aids for software decoder developers. It also includes data trace. Data trace takes the address and data of loads and stores and traces that as well. Okay, so let's just, I guess, take a little worked example here. So, trace begins by reporting the start address. So this provides a sync point for the decoder. It can identify where in the code you are. And from there, only branches, interrupts, exceptions, and so on get reported. So, for example, here we can see, after the start address, the next couple of instructions are sequential, so they're not reported. We have a branch, it's not taken. The next set of instructions are sequential, they're not reported. We have a taken branch, repeat some instructions, and then finally a non-taken branch. And this information goes into the trace output, which allows the decoder to reconstruct what's happening. Okay, so let's look more now at the eTrace standard. So, a successful debug and trace ecosystem requires a group of people working together on a common set of standards. And the eTrace standard is one such standard, and it covers both instruction and data trace, as well as the interface between the CPU and the encoder. And actually, that interface is not specific to eTrace. It's in the eTrace standard because that's where it was devised, but it's equally applicable to other trace standards as well. And most of what's in the standard was originally donated by Siemens or UltraSoc, as we then were, and then refined by the community and ratified. And so here we have a timeline. It's just showing some of the history of that. So it starts back in 2018 with UltraSoc developing the first commercially available trace encoder for RISC V. Shortly after that, there was the trace working group was formed. And ultimately, that resulted in version 1 of the specification being ratified in 2020. So this includes instruction trace only. Further work resulted in version 2, which was ratified in May of last year. This includes data trace. Activity is continuing as well. So in both of these standards focused specifically on the trace packet formats. It didn't standardize the encapsulation that's needed for transport. There are some illustrative examples of how to do that in here, but they're not in a kind of normative specified format. So there's work going on with the eTrace encapsulation task group, which I chair, to codify that into a standard. Okay, so I guess so. The E in eTrace stands for efficient. So this illustrates I guess why that is. So we can see the encoding efficiency is very high, in the order of a tenth of a bit per instruction. And as I said earlier, the efficiency means you can trace for longer or more, and use less bandwidth. So I was going to dig a little bit deeper into the eTrace standard itself and what that comprises. So firstly, it contains a number of mandatory parts. So there's the interface between the encoder and the CPU. There's the branch trace encoding algorithm and the packet format. And then on top of that, we have a number of optional features and enhancements comprising a whole mixture of things. So we have data trace, support for superscalar CPUs that do return multiple instructions per cycle, several modes aimed at improving the efficiency, a few others that are aimed at making easy to debug decoders, and then support for filtering and timestamps and so on. I guess so. The Siemens encoder also has an additional capability which is not currently part of the standard, but I guess is a potential candidate for future work, which is around cycle accurate trace. So So what this means is, as well as being able to determine what the CPU executed, you can determine on a cycle-by-cycle basis exactly when those instructions were executed, or indeed, in the case of a superscalar CPU, how many instructions per cycle were executed. So, continuing with the efficiency theme, I'm going to look a little bit more closely at the options available for improving the efficiency. And the first of those is what's known in E-Trace spec as implicit return, sometimes referred to as a call stack. So, programs typically contain a lot of functions. When a function is called, the return address for that function is pushed onto a stack. When the function returns, that return address is popped off the stack, put into a register, and then you do an indirect jump to that address. And so that's an indirect jump, and indirect jumps normally have to be reported in full in the trace. But of course, well-behaved functions generally return to the instruction which is sequentially after the call. And so you can take advantage of that. And the way you do that is in hardware, you push the predicted return address onto a stack. When the function returns, you compare that address, beg your pardon, with the, let's go back, with the, you compare that with the expected return address, and if they match, then there's no need to generate a trace packet, including the return address at all. And this can be extended further. So if you associate a counter with each stack entry, then you can use this to keep track of recursive functions so that they don't consume any stack resources, and this can give a very significant benefit for most programs. The next option is the branch prediction capability. So branches normally generate 1 bit of trace each to indicate whether the branch is taken or not. But you can enhance that with the addition of a fairly simple predictor. So if you have a branch predictor that you implement both in hardware and equivalently in the decoder, then you can essentially keep track of the number of correctly predicted branches, and only when you have a misprediction do you need to report, and you output the count of correctly predicted branches prior to the one which failed. And this really benefits programs with lots of loops, particularly tight loops. We then have a jump target cache. So if you have functions that are called repeatedly, when the function is called, if it's called with an indirect jump, you can put the address of that jump into a cache. If the same function is called again later, and the address is in the cache, then instead of reporting the address of the target, you can report the index number of the cache entry, and it's typically fewer bits, and so you get a more efficient encoding that way. And then finally, there's a sequential inferable jump mode, which takes advantage of some of the kind of instruction fusion that you can get with RISC V. So, instruction pairs such as LUIPC and JALR, which add a constant to the PC, put that in a register and then jump to it, can be treated as inferable, because all the information here is in the source code. It's just spread amongst 2 instructions rather than being in one. I guess so the next thing I want to show is some results. So we ran you don't need to digest this table. I've got some nice graphs. But basically, we ran the MBench benchmark suite against the encoder with the optional encoding improvement modes both turned on and off. And from that, you measure the bits per instruction of trace that are generated. And here we can see some of the results. So first thing to note here is that there's a very wide range of encoding efficiencies. It's very dependent on the particular nature and characteristics of the program. Some programs are much more compressible than others. The second thing we can see here is, so in the dark green, we've got the encoding efficiencies of the basic mandatory features, and then in the pale green, with the optional efficiency extensions turned on. And overall, there's an improvement here of about 40% in the bits per instruction. Although, it varies between, so it's always better, but sometimes not by much. And then you get cases where it's a lot better, in some cases, extremely extremely a lot better. And then we can analyze this a little bit further. So the next thing we can look at is how that breaks down amongst the different optional modes. So we can see actually that the biggest contributor to the improvement is implicit return capability. And on average we see somewhere around about 36% here. Actually, even with a stack which has only room for one address, you get well over 30%. So most of the benefit comes with the simplest hardware implementation. Then as you add a deeper stack, then things improve. So on average, around 36%, but you can see some programs, like the CRC32, we see a 98% improvement in encoding efficiency with this. And then similarly with a branch predictor, maybe around 6% on average, rising to nearly 40 in some cases. I think this case, the predictor's only got 4 entries in it. It's a very, very simple predictor, 2 bits per entry only, so not much hardware involved in that. And then finally, with the jump target cache, again, on average, the improvement is small, a couple of percent, although rising to maybe 10. And this, I think, is 1 or 2 entries in the cache, so pretty small. Okay, so I guess to summarize, we can say, hopefully, it's clear why understanding program behavior is complex and why having a non-intrusive full-speed trace encoding is required. An efficient trace for RISC V addresses this, and the optional encoding modes offer a significant benefit on top of that. I'm going to go further as well, of course, and in the words of my former colleague, who many of you know, Gajinder Panesar, he would say it's not all about the CPU, it's about the system, and actually being able to observe the overall behavior of the whole system is even more challenging, but nonetheless necessary. We have a solution which can help you solve that problem. So the Tessent Embedded Analytics platform has a full RISC V standard compliant trace encoder and a whole bunch of other IP that you can use for system level visibility. And that's the end, so thank you very much. I'll happily take any questions.